There it goes. Okay, so we're working here with Josh. We're trying to make a pretend oral exam just to give you an idea of how it might go down. So a couple of things, Josh, when you're working, it's nice to have a piece of paper handy and a pen in case you want to doodle and make some scratches. And one of the things that's hard for students is you want to just sit there and work on the paper. So sometimes I want you to talk and be like, kind of think it through. And so you may hear me prod you like, what are you thinking? Or just kind of walk me through it. It's okay to make mistakes because sometimes you catch them while you're talking. So if you're like, wait a minute, that does. And so usually I'll let you babble for a while, maybe even, screw up and see if you catch it or not and try and be patient a little bit. So that said, here's a question for you. I just made this one up. This may not be the perfect question, but let's just get an idea for the process. So let's say you have this circuit. Sorry, not circuit. Let's say you have these wires. This is a wire carrying current out of the page. And this is I2. Let's say this is I1, and assume they're the same size current. And let's say there's a point up here. What direction does the magnetic field point up here at this P?
Right, so I1 is going into the page, you said?
Sorry, did I say into? I meant out. They're both going out of the page.
Both are out of?
Okay. Yeah, sorry. If I said into, I misspoke. They're both going out of the page.
So it's going out of the page.
Mm-hmm.
The current should curl around. So I1 should create a force or not a force, a magnetic field to the left from the point. And then I2 also going out of the page should, well, wait, no, not completely to the left. It would be like kind of down and to the left.
Okay, like this?
Perpendicular to. Not that far down. It would be perpendicular to the radius from the center of the wire to the point. Yeah.
Got it.
And then the other wire would go make the magnetic field up and to the left. So it would be parallel to the radius from the opposite wire. So it would be
parallel to
well, parallel to the radius of the other wire, but wait.
I think you meant perpendicular, right?
Oh yeah, because it won't necessarily be parallel to the
parallel
one
would
from
be
the
this
other
way, right?
Yeah, I was thinking to the other wire, the radius from I1, but I guess that wouldn't necessarily be the case.
Yes, exactly. Okay.
Yeah.
So in this case,
perpendicular to that one.
So I probably led you a little more than I was supposed to, but it's a little bit goofy and we're practicing, so that's fine. That said, what is the net field?
It should be to the left.
Okay. So now here comes my question. As you get closer to the wires and you come down here towards the center, what should happen? So let's just call this B total, okay? So let's say you move the point P closer to the origin here. What should happen to the size of B total and to the direction of B total?
See, the size would get smaller and eventually be 0.
How can you tell that?
The point is directly in between, because I1 should, at that point, would be a force directly downwards. Yeah. So I1 would make a force directly downwards, and I2 would, or not a force, magnetic field.
Good. And you keep catching that. That's good. So I've noticed, and I just kind of let you talk, but you keep correcting yourself, which is good. So you said this is a field downwards. Is it bigger or
downwards?
Yeah. Is it bigger or smaller than the other one up here?
It should be bigger because it's closer to the wire.
Mm-hmm.
And then I2 should create a field directly upwards.
Bigger or smaller?
Bigger.
How does this one compare to this one? Whoops, sorry, B1. Oh, this was B2, sorry. But how does this B compare to that B?
They should be equal, assuming that the current in both wires is the same.
That's right. So now what do you think would happen to the direction as you go downwards? Let's say we pick some point in between.
It should stay the same, shouldn't it? To the left.
Okay. Well, what if we go below here?
Then below, is that supposed to be still on axis?
Yeah, still on axis. Sorry. I'm kind of drawn from the side there. Sorry. Let's say we pick a point that's on axis below. Is that going to change anything?
Let's see. I1 would create a field down and to the right, perpendicular to the radius to I1.
You said down and to the right? So that way?
Yeah.
Yep. And then what about the other one?
I2 should create a field up and to the right, perpendicular to the radius to I2, which those forces should combine to create a force directly to the right.
And then, of course, what do you think I would say about you saying force?
Field.
Yeah, I got the idea. All right. So if you tried to plot this, can you try to sketch what a plot of the magnetic field in the X direction would look like versus Y? So this is what I want. I want you to plot BX versus Y. And so maybe we'd have it like this. I don't know if you could see that, so let me go to speaker view. Whoops. So what would the magnetic field in the X direction look like as you change Y coordinates? Can you sketch that?
So on both sides, both negative and positive?
Yes, some over here and some over there. And if you want, you could just take a second to doodle it on your paper and then hold it up to the screen.
Let's see. So when it's negative, it would be graded. Let's see, at P, the original point, it should be the greatest. Wait.
You don't have to be perfect, just the approximate shape. Don't try to get it exact. I'm more interested, like, where is it big? Where is it small? When is it equal to 0? When is it positive? When is it negative? Does that make kind of sense?
Yeah.
So
it should be roughly the biggest at P, but there may be a point in there where it like gets the biggest, and then as P continues being further away, it would get smaller, right?
Okay. So then, so see if you could try and sketch that. Oh, sorry. You need me to be back on speaker view?
No, I can see it fine.
Oh, okay. So I'll just give you a second to just kind of think it through. I'll pause and not talk.
So I'm not sure if it should be linear.
Don't worry about that too much. Just kind of draw it big, small, and where it's equal to 0.
Okay. So it would be approximately, assuming it was linear, but I think it would be somewhat exponential, like that. So it should be something like that.
Okay, and what if you keep going farther out?
It should go back down, right? Because once you get too far away, then it would, like, assuming like P is whatever, like the critical point or whatever, then it should start going down after that.
Exactly,
right?
Something like that. And then it probably wouldn't go down that sharply. I would think it would be something. And let me see that again one more time. Let me just make sure one other thing.
That was mostly just because I ran out of space at the edge.
Okay, there's one thing wrong with your plot. Go ahead, take it down and take a look at my, okay. So remember, we're looking for the X component of the B field as Y changes, and this is the origin. Oh, whoops, sorry. Let me go to gallery view. Sorry, so this is the origin.
Oh, as Y changes.
So as Y goes up and down, when we're at positive values of Y, et cetera, or negative values of Y.
Oh. Wait,
I lost your screen.
I think the power... Yeah, the power just went out at my house, apparently.
Oh my gosh. Oh,
I'm still on... I'm at on my laptop battery power and running off my phone hotspot, though, so... I don't know if you can see me in the dark, but...
No, I can't. Well, let me ask you this. Do you know what was wrong with your plot?
Yeah, it's just backwards. So I think it was confusing me because it was, instead of like the typical x-axis and y-axis, it's like backwards. So yeah, in the negative y, it should be positive.
Correct.
X.
And positive bx. So the bx, the x component of the magnetic field is positive when you're at negative y, and then vice versa. So I would say you did a pretty good job on that. And notice you basically only missed that one little thing on the signs. Agreed?
Mm-hmm.
And so that would probably be a pretty good score. And that's also, you notice how I kind of make the questions a little bit tougher as time goes on because you were answering them correctly. So that's, and this is something that I try to do to everybody is adjust the test to your level. So you're always just uncomfortable and having to think. So that was pretty good. Josh, this is crazy, but do you want to try another one right now just for fun or not? Or you want to deal with the power outage? All right.
Okay, wait, I think it's back. Oh, we're back. Okay.
Okay.
Weird.
There's a lag here, so I don't see the lights on you yet. This is pretty funny. Hopefully everything's all right. But yeah, all right. So let me try another one I just made up. So I don't know if this is a great question or not. It's just the first thing that came to my mind. So let's say we have a circuit here, and you have a resistor here, and we have two resistors here, and then we have three resistors down here. 1, 2, 3. Can you see that all right, Josh?
Yeah, I can see it.
Okay, and then I'm going to go to speaker view so the live stream can see it better. Whoops, let's get me up there. All right, so we got this circuit. We'll say this is R. Let's say they're all resistors are size R for right now. Okay, so my question to you is, if I put another resistor right here, let me put that one in red. So let's say I added another resistor to this branch. My question is, how will that affect the current in this resistor? Or will it?
As far as like just if it increases or decreases or stays the same?
Sure.
So that should decrease the overall equivalent resistance because in just that second branch, the resistance would, because of the inverse relationship, the overall resistance should go down in that branch, which means the overall equivalent resistance should go down, which would increase the current in that first resistor.
Okay. So then what would happen if I instead put the resistor right here? Would that change your logic or not?
Let's see. So that shouldn't affect it at all, should it?
So I don't understand. Just make sure I understand. So how is the current in this resistor affected if I added in this blue resistor?
Well, It. Wait.
And you could talk me through what you're thinking as well.
So, see, I'm thinking that I think because it's in parallel like that, the two branches should be independent. So the current through that one resistor shouldn't change, assuming that the power supply is able to keep up.
All right. Good job. Nice. That was, yeah. So that was pretty fun. That's a slight trick. I'm trying to think if I have another question for you to finish this out here. Let's try one of these here. Oops. Let's make this a little easier to see. So let's say we have a plot of potential versus position. Okay. So in this case, let's say we start with a proton sitting right here. Okay. And let's say this proton is initially moving to the right. We'll say the proton's at x equals 1.0. The units don't matter. Sorry. And then we'll say, so we'll say this is 1.0. And we'll say it's initially moving right. Can you describe the motion of the proton if it's released right there and it's initially moving right? What would happen to it?
So because it's a proton, it has positive charge, so it should behave as if it's like sitting on top of the curve and want to slide down like to a lower potential. Okay. So it should increase its speed as it moves to the right and reach a maximum speed at the bottom of the lowest dip there.
Okay. So it's going to max, you said it will reach max speed here.
Mm-hmm.
Okay.
Then it should
so
slow
we'll call
down.
that about 2.0. We'll call this about 3.0. We'll call this about 4.0 if that helps you communicate.
So then at about 2.5, it should slow down a little bit, but then keep going. And then increase a little more as it goes down the second dip, but not too quite as fast as the max speed because the dip isn't quite as low.
Sure.
So then it should continue up, and it looks like at 4.0, it's about the same height as it started off at.
So what does that make you think? Is it going to make it there or not?
Yeah, so you said that it started off with an initial speed. So when it makes it to that point, it should have that same speed that it started off with.
Okay, and so then will it keep going past x equals 4 or not? If this just kind of goes out like that?
It should go past it, but how far it gets depends on what its initial speed was.
Okay, so where does this thing experience a large negative force? Meaning, to be clear, a large force in the negative x direction, if we're assuming this is the x direction here.
So it would probably, the largest force would be at 4.0 would be 4.0 because it's at it, or no, it would be the greatest slope. Is where it would.
So just kind of eyeball it in your opinion and give me a number. It's okay if it's not exact.
Maybe 3.5.
So this looks like a slope. It's pretty big. All right. What about this region right here?
That would also give a pretty big force, but to the right, towards positive x.
Okay, cool. Now, what would change if this was not a proton, but instead an electron?
So then we could visualize it kind of like a bubble being trapped underneath the curve. So depending on its initial speed, it may make it first past that first dip there. But if it doesn't have enough speed, it may stop before then and turn around and go back in the negative x direction.
And then what would happen if it does go back?
It would, wherever it stopped, it would at the maximum energy there. Then it would go back around the other towards the negative x.
So let's say it could reach this far right here. Let's say this is where it reversed direction. Then what would happen?
So then it should turn around and move to the left again and make it to that same height on the curve when it goes back up.
So like this far, that far?
So it should make it to the same straight across from there.
I think you were so then what would the motion be like in that case?
So then it should continue till it gets to that second point, and then it would the force would overtake the kinetic energy, and it would turn around again, and it should just oscillate back and forth between those 2 points.
Okay, I like that. Yeah, I don't like the phrasing force versus energy, but other than that, that was pretty good. That was excellent. All right.
So it'd be reach the maximum potential or
minimum potential? Well, you could say the force does work to change the energy would be slightly better wording. You know what I mean? So usually we talk about work and energy instead of force and energy, because work, it relates to force, but work is, so you could say the force does work, which opposes the motion or something like that. But in general, it was pretty darn good there. All right. I forget when we started, but that's pretty good. That's 3 questions. And so then maybe we would go to some homework questions, and I'd say, let's try this. Do you have, let me see. Let me pick a random one here. All right. I would like you to show me question. Let me pick a different one here. I don't know. I'm just looking around here. Could you show me question 23.17 from your notes? I don't remember if we had to do that one or not. I can't remember if I told you to do that or not. 17. Is that one of the ones I told you to do?
Was that a slab?
Yeah, that was a slab. What did I say about the slabs? I can't remember.
I think you said not to do slabs.
I think I said not to do 23.17, actually. I think I maybe said do 18 and 19, but not 17. I think that was the deal I made with you guys. Maybe I said do them, but I wasn't going to ask about them. I can't remember now. Do you remember?
Yeah, I don't have 23.17. You
may
have said
18
something...
or 19? Do you have 18 or 19?
No.
Okay, yeah, because I think I said you should do them and look over them, but you don't have to write them up, is what I said. All right, so sorry, I can't remember that right now. How about this? How about show me, I think 22.25 was required. Let me make sure. Yes, 22.25. So show me that one. Yeah, I remember now the slabs we said I wouldn't ask about.
25. Oh, that one, yeah. 22.25. I like this problem. This is a good,
that was a fun one.
The example of how the different things work together.
Okay. So let me see here. Hold on a sec. Okay, there I could see it. Got it. And then, okay, is there more below that, or is that it?
That's it.
That's it. Okay, cool. And this one, all right, so that's pretty good. So let me ask you a follow-up on that one. Whoops, I just lost my page. What number was that? I put my book down. I forgot.
22.25.
Okay. All right. So in this case, let's say you made that half angle a little bit bigger and used the same amount of charge. So in that problem, it looks like this. We've got this angle here, which we call phi, I think. And then there's a point charge over here. And now I think what the question was asking was, actually, let me do it this way. Let me go to here. I'm going to screen share. Ah, come on. Ah. All right, so that was. Sorry, I'm a little slow here. I wasn't prepared. Where was that one? I think it was right after that, right? There it is.
Yeah.
Okay, there we go. So we have this arc of charge. The radius is r. The positive charge q is uniformly distributed. And the point charge q, okay. And so our goal was to make the electric field 0 at the origin, right?
Mm-hmm.
So if, and phi is the half angle. So to be clear, it's phi above and phi below, right?
Yeah.
So that's phi, and so is this. All right, so let's say you take that same rod and you stretch it, and you keep the same amount of charge on it, and you stretch it slightly like this. What is that going to do to the electric field at the origin? Does that make sense what the question is?
Yeah, so the charge density decreases because it's the same amount of charge on a bigger area.
Okay.
So I'm thinking that what would happen is that more of the charge would go into, or like more of the field created would be in the Y direction.
Okay, and if you want, you can annotate on my screen if that helps. And actually what I'll do is I'll make this picture bigger. Let me get it back on there. I don't know if you want to, but you're welcome to. Sorry about it. I interrupted you.
So here,
we stretch it a little bigger. Okay.
So we're going to have some component of, wait, is it positive charge or negative charge? Sorry.
Well, take a look. This one over here is positive, right?
Yeah.
Okay, we're told that the electric field at the origin is 0.
So it would have to be positive.
Okay.
All right. So we're going to have...
I'll call it Q prime just because it's not necessarily the same, right? Okay.
So due to this arc, we should have some component along the x-axis here, and then there'll also be like components up and down that cancel out. So if we increase the arc here, then that should increase the vertical forces.
Okay.
Which means more of the charge goes into that, which ends up canceling out, which would mean that this force should decrease, leading to a net electric field to the left from the point charge.
That's pretty darn good. That's a sneaky little, isn't that fun?
Yeah.
All right, so I'm going to go ahead and stop the share. And so that's an example of how I might ask a follow-up on a homework question. I basically